Okay, so first, what is a zero-G roll? So a zero gravity roll or zero-G roll is a roller coaster inversion where the track twists 360 degrees as it rises and falls in elevation, usually at the crest of a hill. The element gets its name from the weightless effect of zero-G force that a rider experiences during the inversion. The accelerations are due to centrifugal and gravity. Depending on the curve, R, rotation rate, omega, little r, and velocity, the rider may or may not experience zero G's. Okay, so what are these R's? Okay, R is if the roller coaster is going over a curve like this, and it's rotating like this, about some radius r. Omega is the rate of rotation, so it's the angle divided by the time. Velocity is just the speed in this direction of the roller coaster. And here is the revised vertical acceleration equation. Centrifugal due to the rotation, g cosine the inclination angle as usual, and v squared over r is what we've discussed in the last couple of videos. So before I go through the mathematics of this, let's see what it looks like in NoLimits2. Okay, so here I modeled the last 5 meters of the 20-meter segment you just saw. At the start of that 5 meters, the roller coaster is traveling at 53 kilometers per hour, which is 15 meters per second. That last 5 meters, it makes a rotation of 90 degrees, which in radians is pi divided by 2. The radius of the roll is about 1 meter. Okay, so this would be the rotation. The radius of that rotation is 1 meter. The time it takes to complete the 5 meters is distance divided by speed. 5 meters divided by 50 meters per second, or 0.33 seconds. Now I can get the angular velocity. That's the angular displacement divided by the time. So pi divided by 2 radians divided by 0.33 seconds is 4.8 radians per second. This is the centrifugal term due to the rotation. So I'm going to plug in 4.8 for omega here, and I'm going to square it. Multiply that by 1 meter. That gives me 23 meters per second squared. So this is units of acceleration divided by 9.8 meters per second squared. And that gives me 2.4 G's. So due to rotation only, the rider will experience a centrifugal acceleration of 2.4 G's. Now I'm modeling this over a straight line. So I can ignore the effects of centrifugal due to the curvature of the track. So for vertical acceleration, I have acceleration due to the rotation, 2.4, and acceleration due to gravity. Now at this point, gravity is down. So centrifugal and gravity point in the same direction. I add them. At this point, centrifugal is up and gravity is down. I subtract them. So at this segment of the track, the passenger will experience a vertical acceleration between 1.4 G's and 3.4 G's. Where the vertical accelerations can really get crazy is when you're combining rotation, a roll, and centrifugal due to the curvature of the track, and then gravity, of course. So if the rotation rate is high, the velocity is high, and the radius of curvature for the curve is small, these can get extremely high. circular and teardrop roller coaster loops. So I'm going to start with circular, which is relatively simple. So let's assume a passenger is in a roller coaster car and decides to undo the restraint. How fast would the car have to go such that the person would not fall out at the top? Okay, so we're back to vertical G equation. Okay, at the top here, centrifugal is going this way, gravity is going this way, so minus G cosine of the angle there is 0, so it's just G. So you need V squared over R to be greater than G. So given the radius of the turn, you simply solve B is greater than the square root of G times R. So here I've got 3 loops. It's a teardrop loop, circular loop, circular loop. This is radius of 20 meters. So radius of 10 meters. And the distance from here to here is 20 meters. Okay, you can't say it's got a radius because the radius of a teardrop loop changes. Obviously, the radius of a circular loop stays constant. So why do we rarely see circular loops in roller coasters today? If you would like to pause the video and discuss this with your class or think about it yourself, go ahead and do it. We'll come back and discuss. Okay, the reason you don't see circular loops in roller coasters today is because the difference in vertical acceleration, it's called delta acceleration, in the vertical direction, is 6 G's regardless of the radius of the loop. So let's say the roller coaster circular loop is designed such that at the top you're weightless. So centrifugal is equal to gravity but in opposite directions. At the bottom, therefore, you would feel a vertical acceleration of 6 G's. That's a huge difference, and 6 G's is a very uncomfortable amount of G's. Teardrop loop, on the other hand, for this particular teardrop loop, the difference between the top and the bottom is 3.5 G's. So if you structured this such that you were weightless at the top, you'd only feel 3.5 G's at the bottom. Not so bad. So why is that the case with this? Well, as you can see, the radius of curvature changes. At the bottom here, where the speed is the highest, you've got a very large radius. Right? Here's the inscribed circle for this point. Right? That's a very large radius. Up here, it's a very small, relatively smaller circle and a much smaller radius. Now I'm going to discuss the physics of a circular loop. This equation can be derived from Newton's second law for constant acceleration. And gravity over short vertical displacements can be assumed to be approximately constant. For this application, the acceleration is gravity. Okay, I'm going to substitute G for A here. And the difference in the y-coordinate between here and here, delta y, is simply 2 times the radius. So this distance here is 2 times the radius. So this equation becomes this equation. So what does this tell me? This tells me that if I know the velocity at the bottom, I can square it, and I can subtract 2g times 2r. And if I square root that, I can get the velocity at the top. Vertical acceleration at the top, v squared over r plus cosine of the inclination angle. Inclination angle at the top is 0, so this just becomes g. Okay, I'm going to substitute this for this, and I get this. So the velocity at the bottom squared minus 2g times 2r, which is 4gr, divided by r minus g, gives me this equation. So the vertical acceleration at the top is equal to the velocity at the bottom squared, divided by the radius of the curve, which is constant, minus 5g. The vertical acceleration at the bottom is the velocity at the bottom, v squared over r, minus 1g. At the bottom, you're just 1g. So there you have it. If I know the velocity at this point here, and I know the radius of the loop, I can compute the vertical acceleration at the top, and I can compute the acceleration vertical at the bottom. So next I'm going to plug some numbers into these equations. Let's assume at the top you want the passenger of the roller coaster to feel weightless. So the acceleration at the top would be 0. What would be the acceleration at the bottom? Okay, I'm going to put 0 here for acceleration at the top, and that's equal to this expression that I derived on the previous page. I'm going to solve for v bottom squared over r, and that's just going to be equal to 5g. I'm going to plug 5g in for this expression to get the vertical acceleration at the bottom, 6g's. So at the top, the rider will feel weightless. At the bottom, the rider will feel 6g's. So there's a mathematical proof of what I claimed at the beginning. Let's try another example. Let's say at the top, the rider wants to feel her normal weight. So at the top, the rider's sitting on a scale and she wants to weigh her normal weight. So I'm going to plug 1g in for acceleration at the top vertical, subscript v. Okay? And I'm going to solve for v bottom squared over r, as I did before. That means centrifugal at the bottom is going to be 6g's. I'm going to plug that into this equation. Of course, passenger's going to feel her normal weight at 1g, so she's going to feel 7g's at the bottom. So at the top of the loop, she feels her normal weight. At the bottom of the loop, she feels 7 times her normal weight, a difference of 6g's. Again, ties to the claim I made at the beginning. So that's the problem with circular loops. The difference in the acceleration between the top and bottom, regardless of the radius, is significant and uncomfortable. Right? This could be any r. It doesn't matter. Teardrop loops. So the physics of teardrop loops has been well understood and applied since the early 1900s. Lots of material on the web on this topic if you want to learn more about it. But the idea is to have a smaller radius at the top of the loop and larger from top down, simply so that the difference in the g's from top to bottom is not so large. So here is a teardrop loop I generated mathematically in Excel using a system of equations I will show you. And I designed this curve so that the centrifugal acceleration would be constant at all points along the curve. So how is that possible? Well, as you rise vertically, this equation tells us that the velocity will drop. That's easy, right? If you throw a ball up in the air, the higher it goes, the less its speed. The two circles I've inscribed for this demonstration include this circle at this point in the curve with an approximate radius of R1, and this circle inscribed at this part of the curve a little higher up with a smaller radius R2. So velocity is dropped, the radius is dropped, and I've structured this curve such that this remains constant. So higher velocity, greater radius, centrifugal acceleration. Smaller velocity, smaller radius, the same centrifugal acceleration. Solve for R. R is equal to v squared over centrifugal acceleration. Combine equations 1 and 2. So I'm going to substitute this for v squared. I end up with this equation. So this is giving me the radius as a function of y, and these are established values, assumed or entered values. So this is again from the prior page. For small angular displacement, d theta, this is true. R d theta is equal to ds, and ds is approximately straight for very small change in the angle. And we're assuming here that the angle is in radians. Next, I combine 3 and 4. I substitute this for this, and I get this equation. Divide both sides by this expression. Now I have an expression for the change in the angle of this curve given a change in this segment divided by this expression. So it's pretty easy to generate this curve. You simply need to establish initial values for the centrifugal acceleration, the initial velocity at the bottom here, some small change in the segment there, initial values of x, y, and the initial angle. These expressions are also useful. I created a spreadsheet to generate XY values for a teardrop loop based on the equations I derived previously. And here's what it looks like. So here's my d theta equation right here, dx and dy. So using those equations and initial values for the velocity at the bottom, a small ds, and a centrifugal acceleration target starting here with 5 g's or 49 meters per second squared, generate these values. And this is what it looks like. I've actually highlighted a lot of cells that's showing you a couple loops here. The average radius from an angle of 0 to 180 degrees up here is 6.13 meters. And this is about, say, 12 meters tall. Okay. So if you want this initial velocity and you want this amount of centrifugal acceleration, you're stuck with a teardrop loop that looks just like this, 11 meters tall with an average radius like this. And look at the values of the radius. Down here, it's 8.16 meters. As you move up the curve, it drops, right? Because as you move up the curve, the velocity is dropping due to the deceleration due to gravity, all right? At the very top, it'll be the smallest, all right? So up there, you're about 180 degrees. Let's go down to 180 degrees. Let's see it. This is in radians here. Here I've got it degrees. So column K, go down to 180 degrees. And I should have my smallest value for the radius. 3.67, okay? It's the smallest, about 180 degrees, the smallest Okay, again, it makes perfect sense. And that's what a teardrop loop is all about. You'll have the smallest radius where the velocity is the smallest to provide a constant centrifugal acceleration throughout the entire loop. What about if we change this to 3 Gs? Okay, now it looks like this. Does that make sense? Well, now it's taller. So now at 15 meters tall. And the average radius is increased. So that does make sense. Okay, it can go higher because we don't need as much velocity to generate 3 Gs versus 5 Gs. And it can have a larger average radius. Again, because we don't need to generate as many Gs.